Good morning, everyone. Thank you for joining Jetoptera's update webinar. Very happy you're here. Now, before we get started, a legal disclaimer: nothing in this presentation constitutes investment advice. Any money invested is at risk. We hope you will review the terms and conditions on Wefunder and thoroughly review the opportunity before investing. And we're recording the session, and if people can't stay for the full session, the recording will be made available after the webinar. And with that, Andrei Evulet is going to get started on the meat of the presentation.
Thank you, Simina. Hello, everybody. I'm Andrei Evulet. I'm the CEO, CTO, and co-founder of Jetoptera. Today's webinar is a presentation of the material that I presented about a month ago to the AIAA Pacific Northwest section, where after about 6 years from the last presentation, I updated mostly technical folks on the progress we had on the Fluidic Propulsive System. You see here a picture of the, and I must apologize for my voice. I have been traveling internationally recently, and as always, probably I caught a bug from the plane, but I'll do my best here to hopefully everybody can hear me right. This is a picture of the current status of the J500 propulsion system, and I will go in more detail on this. Basically, this is the meat of the presentation for today, with the agenda going over again a little bit over the Fluidic Propulsive System, how it works, what the development progress that happened the past 3 years, platform and near future, and a very important comparison with hybrid electric. And then we'll leave some time for Q&A. I will also give you an update on the recent developments for the DARPA Pegasus team, which is one of the applications we're very excited about participation in the DARPA Lift challenge. Just to recap, we are quite a unique propulsion system for aviation that consists of a device that receives a compressed air from a turbine. We're energy agnostic, so we could use electricity to drive a compressor or air inlet compressor that sucks in air, pumps it up to a certain pressure ratio, and then distributes it to a manifold that has electrically driven valves, and these valves distribute the compressed air to various devices distributed along the airframe. In this case, you see an example with one of the largest thrusters, the largest thruster we've ever built, up to 300-pound force FPS thruster, and that eventually will weigh only about 10 pounds. So the idea here is that a gas turbine will drive this compressor. The compressor will supply the compressed air, and we distribute this compressed air according to where is needed, when is needed. These devices are the secret sauce, so to speak, of our technology, the core of our technology, because they transform a trickle of compressed air with a certain amount of entitlement to make thrust to a much larger thrust, as you can see in this graph. The idea of using an ejector is not new, has been tried in the past. As you can see, this is a compilation of data taken from the past, I'd say almost 70 years of testing with this kind of devices. However, we have put to work advances in CFD, in advanced CFD and advanced material processing and 3D printing to obtain something special compared to what was done in the past. And what you see here is basically just to explain simply, this is a pressure ratio of the air on the x-axis versus the so-called thrust augmentation. What this thrust augmentation is basically is the device that we're talking about here, the ejector, will actually take a trickle of air that, let's say, you're entitled to make 1 pound force of thrust. But with this addition, with this manipulation, if you will, of the air, with these tricks we have, we actually entrain more air and create more mass flow rate than the original one. So much so that we entrain up to 15 or maybe 20 parts of air and moving them slower, but creating more thrust. And this augmentation ratio is actually, if we created 1 pound force with the original trickle of air, then we would create between 2.1 and 3 pounds of thrust for each of this unit of air that we put in. On the y-axis, we have this thrust augmentation, and as you can see, historically, people have been able to achieve mostly under the factor of 2, so between 1 and 2 augmentation ratio. Whereas we have demonstrated that we can achieve for the 75-pound force class and the 250-pound force class over 2 to 1 augmentation ratio. That itself is very important in the vertical takeoff and landing world, because then we can actually augment the thrust we create at takeoff and hover and landing. So we're positioned very well against the historical data. Where we want to be in the future is this area highlighted here in green. So there is room for improvement for lower pressure ratios to produce even further thrust augmentation, which will immediately result in lower fuel consumption and more efficiency. A description of the key elements of the fluidic propulsive system. What we have is the system that I described, the turbine, gas generator that drives a turbine that drives the air compressors. The air compressors take air in and supply this air to a manifold. This manifold distributes the compressed air to 5 locations, 5 thrusters, 3 in the front that are fixed and 2 in the back that are mobile, they're swiveling. In the front, we will employ these thrusters only for vertical phase of the flight. And they are all modulated by valves. So each of these thrusters have an electric valve that modulates and sends more air or less air. And that's going to become very interesting in a future slide because of the response time of this pneumatic system. So the way this works is the turbine drives the compressors. Both compressors pressurize this manifold, and the manifold, then we control how much flow goes to each of these thrusters, and each of these thrusters will generate more thrust than you're entitled to with just that compressed air. And if that sounds complicated enough, hopefully that's not as complicated as it sounds. But basically, it's about entrainment of air, and it's about multiplying the force that we're otherwise generating just with this compressors. There's an additional, excuse me, high-speed nozzle here. So this is the rear of the aircraft, and this is the front. This pipe that you see here, my cursor is also used for the high speed. So basically at the high speed, we shut off, isolate the front thrusters, and we don't employ them. All the air is going to the back through this carbon composite FPS thrusters, 250-pound force class, and through a nozzle that will operate just like a simple turbofan. So you have 3 jets at high speeds, and all of them contribute to forward flight. And this gives us the edge over other systems. We have no blades, and therefore we have no limitation, real limitation in going forward. we can go 2 or 3 times faster than a helicopter, which will encounter all kind of issues with the tip of the rotor. The free turbine compressor 250, it's a 250 kilowatt system that we are employing on this first demonstrator. It was developed from scratch. It is actually an axial compressor supplying the primary air. So what you saw here is this section right here. It's an ultralight design for adaptive operation, supplies air to FPS thrusters or compressed air in direct fan operation. That's that high-speed pipe that I described. The system is titanium alloy built, and it's got elements also of 3D printing. It's very simplified in the terms of lubrication. For instance, we have greased bearings that do not need a lot of maintenance, and it's easy to swap. The system is very modular, so you can swap it back and forth when you operate it. So different modules are interchangeable. Here's the test. So there's a lot of work that went into the past 3 years in terms of CFD, advanced turbo machinery, as you can see in the top here. On the bottom, you see a video of the recent tests done at Inan in the United Arab Emirates, and you can see the silhouette, if you will, of the turbo compressor with the test being conducted for mapping the performance of such a compressor. So without getting into a lot of details, what mapping of a turbo compressor means is that, as you can watch this bright spot moving along a line, that's the operation line. And what you have here is mass flow rate on the abscissa, on the X line, and on the Y line or ordinate, you have the compression, the pressure ratio. At takeoff, we want to accelerate this FTC, this turbo compressor, to operate somewhere at high pressures and high flow rates. This in turn will result in a lot of thrust created statically to take off vertically. And then at cruise, we will revert to, so once we transition to horizontal flight, we will park the performance point to a lower pressure ratio and a lower flow, just as needed for forward flight. This is a map that is very classical. It's been around for, this type of charts for performance have been around for 100 years in turbo machinery and compressors work. So there's nothing new here. It's just the way we operate and we optimize the system. So we get very high efficiencies. In our previous work with Pratt and Whitney on the high-speed VTOL challenge program, Pratt and Whitney confirmed that efficiencies of over 90% are doable on systems that are more than 1,000 horsepower. So we look very good in terms of efficiencies of operation in flight with such turbo compressors. The manifold contains this key elements called valves, butterfly valves, to be more specific. These valves are critical in operating the entire system because as they open and close, they distribute the air from central source, this turbo compressor, to the thrusters. We have found very interesting performance levels from this. This valves are actuated electrically by servos produced by a company in Germany called Volts. Maybe you saw some updates there from my recent visit 2 weeks ago to their facility. They're very excited to work with us. We have studied this manifold quite significantly with CFD and testing to understand any losses that occur from the friction of air to the pipe. And thanks to our friends at Aerotech, they have done a marvelous job in making the manifold extremely light. What you're looking at here is the central piece of the manifold that weighs only about 1.4 pounds. So it's an extremely light system made out of aluminum. We don't need it to make it out of heavier metals because the pressure and the temperatures of the air produced by these turbo compressors are benign enough, so we don't burst them open or have any kind of overpressure. And the pressure loss to the most distant place, which is basically the front thrusters from the turbo compressor, is less than 4%, which this number may not mean anything to you, but it's a very low number in terms of delivering a high efficiency to the entire system. As I mentioned, we employed very accurate and very fine-tuned and calibrated CFD. This is one of the things that makes us very confident. We have tools, we have developed tools in the past 10 years that are very accurately describing the system, the pressure losses, and the flows. One of the discovery we did last year was this amazing property that the response time of our actuating the valves is extremely fast. What it means is that when we're running a test or we're in hover, let's say, and we have a gust of wind, this actuation of the valves result in immediate distribution of or production of the thrust in less than 50 milliseconds. And what we did here to find that was to actuate the valve during one test at various frequencies, which you can see here, close, open, close of the valve, and then to see the response time of the thrust. As you can see here at higher frequency, the valve opening and closing. And why is this important? It's important because we can respond to a gust of wind or any perturbation with about 1 order of magnitude faster than a similar system with rotors or propellers. So, typically a quadcopter or any of these eVTOL systems that employ rotors respond in about 200 to 500 milliseconds to a command to change something, to change the load on the propeller and to change the thrust. That is very slow compared to us. In less than 50 milliseconds, we respond to such a thing, such a perturbance, and we can therefore control the aircraft much faster than any of our competitors can do. We fine-tuned the CFD of all of our systems. You see here two examples. One at the bottom is the volume of the CFD for the J500, but on the top it's from a different project, a powered parafoil project that we worked in the past. And most importantly, we have a lot of data that calibrated our CFD. CFD is useless without some calibration. So we've spent many hours in getting the data, experimental data to validate our tools. And that makes us special because now we can talk about using these tools to further scale up our systems with very reliable tools. This is something that was lacking in the past. In the 60s and the 70s, when they were trying these ejectors, they never had a calibrated tool, CFD, and that's why they abandoned that path. But we are today the only, as far as I can tell publicly, the only company in the world that is working on ejectors and has tools to develop these ejectors properly. Also, since last time I updated AIAA, we have conducted a number of tests with, thanks to our Aerotech company. All these components have been meticulously evaluated as separate elements by Aerotech. Aerotech is a company here in Seattle that specializes in certification of flight components as well as entire aircraft. This is one of the most capable companies in the US and probably in the world, and has in the past been employed by Mitsubishi, for instance, to certify their brand new Mitsubishi regional jet. That was about 2019, 2020. Certification they did with the FAA. It is very likely that we will employ the company Aerotech for the certification under Part 108, which is, for instance, the cargo drone we're developing under a different program, but also for the J500 and for the manned applications that will, the Mosaic new FAA initiative. So we're very likely to collaborate further with Aerotech on those opportunities. What you're looking at here is the single test measurement of the thrust of a 250 pound force class system. And then on the center here is the 75 to 100 pound force class. These are the front thrusters and these are the rear thrusters. The rear thrusters, as you recall, are swivelable. The front ones are in a fixed position. Further, we are in the phase now where we're testing in Dubai. At the bottom here in the left corner, you see the system, the FPS system currently in Dubai at the Inan facilities being tested with the turbo compressors on and characterized there statically. But to get there, we evaluated the thrusters at Aerotech. We evaluated the turbo compressor for mapping. And now the next steps will be the static tests on the fuselage. So the entire system will be transferred on the fuselage, then followed by the tethered hover tests, free hover, and full missions by Q3 of 2026. There's a video here on the floor of the Inan factory with the system being prepared for another test. These are two employees that are preparing for, and actuating, making sure that all the servos are working properly, all the valves are opening and closing. And obviously after this, they would run a test. One of the things that I updated AIAA and the audience was also on the acoustics. As a reminder, we have conducted thorough investigations of our thrusters versus other technologies. As you recall, one of the main characteristics of the FPS is that the thrusters are atonal. They form no tones because we don't chop the air. And here's a reminder of a graph, and this is what I reminded to AIAA, which triggered a lot of interest and questions. A comparison to two technologies, an electric ducted fan and a propeller, electric propeller, at the same levels of producing the thrust measured in an anechoic chamber. And you can see here the blue lines, it's basically a graph of tones and intensity of the tones of the noise versus frequencies. The blue line is actually the propeller because it's moving slower than anything and chopping the air at the slower frequencies. It produces these tones that are traveling very far in the atmosphere without any abatement by the atmosphere. So the atmosphere does not absorb that noise because it's a low frequency. That's the reason why typically a propeller or a rotor of a helicopter is being heard from many, many miles away before you actually even see the helicopter. Now, for the reddish line, those are the frequencies of the electric ducted fan. And you'll see companies out there that say, okay, we move to the right, the higher frequencies, the tones. You're still chopping the air. So an electric ducted fan is obviously sounding more like a dentist drill, higher frequencies, tens of thousands of RPM. But that's still very annoying and very much in the range of human ear hearing it, but particularly for animals. Dogs would hear that much better. Dogs and cats would hear that much better and would be annoyed by that. Now, this curve that you see no peaks of, that's our curve. That's the FPS curve. And because of the lack of any tone, we are actually automatically 30 decibels less than any of the other technologies. So basically, we are, as Dr. Robert Doherty, the AIAA prize, acoustics prize winner in 2019, said, it is important to know that your device as comprised so far will not sound like a machine. It will sound more like wind. This is just simply background noise. So this is something that we intend to exploit, obviously, and it's an advantage that we have over our competitors. Now, one of the things that I addressed during this session was the emergence of fascination of many of our competitors with hybrid electric. So the chapter of battery only is kind of closing right now. People have realized that the battery is heavy. They have not been performed so well in terms of increasing that specific energy. And now everybody's talking about shifting to hybrid electric. Well, a hybrid electric system is basically a turbine in general, or could be a piston engine that drives a generator that drives an inverter that uses a smaller battery, somewhat smaller battery that's being recharged at all times. And then it generates this power, electric power, that is then being distributed. I caution the audience about the fact that you're opening another can of worms on the hybrid electric in terms of that introducing so many other systems and subsystems that all of them need cooling and all of them need auxiliaries that perform this heat transfer. You end up with a rather monstrous system that is 3 times heavier, twice as expensive at least, and with efficiency that eroding the original turbine that drives this generator, et cetera, et cetera. So I made these remarks by doing a comparison of 3 systems, 1 megawatt based. So that's a very typical air taxi kind of size of a turboprop. So that would be an original turbine that drives a propeller, directly a propeller, with an efficiency of 26.6%. With a turboshaft hybrid electric. So you take the same turbine and then instead of driving directly a propeller, you now drive a generator, an inverter, a battery, then you have transmission lines, then you have electric motors distributed across the airframe, all of them needing liquid cooling, so a pump, each one of them has a pump with a liquid on board, et cetera, et cetera. So you're generating less efficiency compared to the original engine, 23.6%, whereas your weight has tripled at least because you're carrying along all the systems. And that compared to a 1 megawatt fluidic propulsive system is very simple. We are the shortest path from fuel, chemical stored energy, to actually producing thrust because we have this ultralight system that adds almost nothing to the original turboprop. In fact, we're reducing the weight of that because we are eliminating the reduction gear that is typical of a turboprop, for instance. And then our efficiency is slightly better than a hybrid electric. We're much lighter, and we are therefore efficient, and we leave more room, which is very important. The fraction of the propulsion system on board of the aircraft is much less than in the case of a hybrid electric propulsion system. This is very important because nearly, in fact, 99.9% of our competitors are using now hybrid electric systems, and we will win that race because we will be able to put more payload and more fuel on board, therefore being able to go further in range and carry more with our system rather than having a system like a hybrid electric one, which is very complex and prone to failures, single point failures as well. Why is this important in terms of weight? It's very important. The weight of the aircraft and the weight of the propulsion group on board of the aircraft is very important, and that was actually illustrated back in the First World War, when an engineer, a French engineer by the name of René Devier, has calculated, and by the way, this work was secret back in 1916 because he was calculating the range of French bombers that would attack German positions. So this engineer applied math that is still applicable today, believe it or not, about the range of an aircraft that varies logarithmically, so non-linearly, with the range you can achieve. In other words, the higher the fraction of the fuel on board of an aircraft, the further you can go in terms of range. And that was considered secret at the time. As always, an engineer name is never making it to the Hall of Fame, but instead his friend, René's friend, Louis Breguet, has actually promoted this approach and explained the benefit of putting more fuel on board of the aircraft. And for those who are interested, you can still buy a 1918 edition of Dynamics of the Aeroplane, written by René Devier, in which the Breguet range is being explained. So it's extremely important to put more fuel on board because as you get lighter, you fly more efficient and you fly further and further. What is the effect of that? If I compare a 1 megawatt turboshaft hybrid electric with a 1 megawatt fluidic propulsive system, these are the numbers. We would go at least 25% range longer. We will burn fuel at 10% lower rate than the hybrid electric. The weight of the propulsion group would be 50% lower in our case. Cost, because of all this auxiliaries and all these other elements, motors, inverters, etc. All this cost a lot of money. We are much simpler than that. And the operational cost, which will be transferred basically to the customer eventually, is going to be about 75% lower. These are very mathematically well understood numbers. And obviously, our technology, which is, as a reminder, we have 189 patents awarded to date. This technology that we have is quite unique, and we have a nice moat around the technology, and so we can protect it, and we are the only ones who can use it. Good. So now we move into the other project that I want to give an update on, and that's the DARPA Lift Challenge, the Pegasus. As you recall, over the past 5 months, very intense months, we've been very busy demonstrating pieces of the technology and putting it together. Starting with the tests we conducted in February and March of the propulsion system that we developed. This is a much simpler system in that we're not using a turbo compressor. We're just using the small turbines to use the hot gas to drive the fluidic propulsive system. The reason we went to that approach is because we have to keep the entire system to less than 55 pounds or 25 kilos in SI units. It has to lift at least 110 pounds payload, and it has to complete per DARPA 22 turns over 4 miles. So that's kind of a mission that everybody's scratching their heads about. We would prefer, going just around, and that's how we're going to start the test by just going around 4 miles to show DARPA that basically we can do this. Were it not for a complete crazy mission like 22 turns. But we're going to attempt, obviously, to do both. We are very well positioned because we are developing systems that are ultralight. The power of the turbine is undisputable, and we can pack a lot of power in a very light system. To that end, we are using ceramic matrix composites made also in Germany by a company called Walter Prisco. And we've collaborated with them, if you recall, on testing on our glider, our flight test platform. And we are employing these as well. And with that, I want to go into the presentation of an update on that Pegasus based on my recent trip in Germany. So, of course, we used a little bit of description of what Pegasus is, their artistic view. But basically, why do we think we're going to be a winner here is because we have developed a unique VTOL capable propulsion system that is this adaptive fluidic propulsive system. It's extremely light, and it's based the only one in the world that we're aware of based on ejectors to minimize weight and augment thrust in a very small package. These turbines are now used as gas generator using jet fuel. We will be able to achieve unique high-speed wing-borne capabilities with efficient VTOL capabilities. That's something that, for instance, a large rotor, which we think are going to be the other competitors, will not be able to achieve. We have developed a unique control system that controls aircraft attitude 10 times faster. Remember what I mentioned about the valves and our discovery from last year that we're 10 times faster response versus multicopters. We use unique materials as I described the OCMCs. By the way, there's only 2 companies in the world that actually fly with CMCs, and those are GE and Safran in France. The CMCs are 1/3 the density of steel and have high temperature capabilities, making them ideal for this application with use of gas generators. This gas coming from the gas turbines is slightly pressurized, and it's about 1200 Fahrenheit, 650 Celsius temperature. We will create smaller outwash than turbojet system. That's another platform that we think are going to be our competitors in this DARPA challenge. But overall, it's a compact design with no blades or props that is truly runway independent. So this is a description of what we did so far in the past 5 months. This was also transmitted. This was presented to DARPA Lift Challenge. We started with a static test of the system. Here, in this case, it's upside down for reasons of measuring the thrust. This platform has been measuring the thrust with the use of load cells. This is only half the system, so to speak. And this was tested in the United States in February. Yours truly is controlling the flows here, controlling the turbine with Sean, our engineer, taking notes and making sure that we collect the data. Again, we're the only ones that will use non-prop, non-rotor systems for this challenge. So pretty excited. We think we're in a very good position to at least win the most unique propulsion system that comes with $500,000 DARPA award. But we're looking forward to compete successfully. Now, the controls of this thing is also very important. And to that end, we have been developing the controls on an electric system to autonomously control the platform. So in this case, we use the electric ducted fans just to perfect the controls, the brain, if you will, of the system. Which we did. As you can see, we placed the batteries on the floor because they're very heavy and we couldn't take off with that. By the way, this DARPA challenge we think is going to be a no-go for anything electric, simply because the battery needed for that mission to turn 22 times is just too heavy and is going to put them over 55 pounds, the weight of the aircraft. So this is filmed in Germany a week ago. I traveled there where we put together the frame. It's like I'm happy to report tremendous progress here. You see here a carbon fiber frame that holds everything together. You see the control system that I just showed you in a video with an electric now transferred to this system, and the frame is ultra light. It weighs just shy of 2 pounds, the whole thing. The ceramic thrusters use titanium aluminum alloys, very light. There's the two engines on board, procured from JetCat, another German company. They act as gas generators. Then you see the cube. That's the brain of the system. This is basically the flight controller that will dictate which valves are opening and closing at what time to control the attitude of the aircraft. This also controls the throttle and the RPM of the engines themselves. We have a large number of servos on board. Like you see here, each of the servos, there are three of them. One is under this extender, can extender. And you see the valves here, 1, 2, 3 at this end. This servos are controlling the valves in opening and closing. The number 5 here is, for instance, for one of the thrusters. The one in the center is for the high-speed nozzle. So again, just like in the case of the J500, we're controlling the hot gas this time. As you can see, opening and closing in sync, the vanes and the control valves. Let's see. Then we have the thrusters, of course, which we have already tested. This is another thing that is very lightweight. These are literally the fuel tanks or bags specifically designed to be very light and contain the volume that we need for the mission. And then there's the servos that control the valves, the flaps at the end of the thrusters that will redirect the efflux coming out of the thruster. So the efflux coming downwards after entrainment on the top, the air is being mixed with the hot gas and it's coming out at a mild temperature of 200 degrees or so due to the mixing. Now, the other thing is, I'm proud to say that we are now at 21.14 kilograms for the entire system, which is about 46 pounds. This is including everything. So this is an amazing number, and it's going to play a role in the Part 108 because we will be able to build a 110-pound aircraft that can carry a lot of fuel and is going to be less than 55 pounds in hardware, making the usable payload, meaning a combination of fuel and payload, cargo, for instance, available to perform much better than, for instance, Amazon Prime's Mark 30 drones. So we will be able to go much farther, carry 50 pounds of payload if need be. Remember, as a reminder, Amazon Prime is only able to deliver 5 pounds or less, and only 7 kilometers away. We will be able to do 25 miles runs with 50 pounds of payload down the road. So my point being that this development that we're doing for DARPA is not only important for DARPA and is not a competition only, but it will result in another product of Jetoptera that with a simple design can actually outperform anything out there that's electric or hybrid electric in the Part 108 system. So we're very excited about this. You see the valves at work here. Again, validated by the controls. And as of last week, we put this on a tethered and we started the testing. We have some bugs to debug, but that's very typical of the system. We're very optimistic about running these tests with tether mode in May, free flight with transition in June, increasing payload towards target in July. And in June and July, we're going to run this test at Pendleton in Oregon. So we'll bring the system here and we'll be ready for the competition in August, which is in Ohio, Dayton, Ohio, at the U.S. Air Force National Museum. And with that, I will wrap it up here with the conclusion that we have two FPS prototype demonstrations planned for 2026. Both are VTOL. One is the J500, the larger program with Enon, our collaborator in Dubai. FPS offers, and the other one is the DARPA opportunity. The FPS offers attractive alternatives to hybrid electric for conventional short and vertical takeoff and landing, as well as winging ground effect. The production of J500 is planned for 2027, and we have seen interest from potential buyers and customers in Asia and the Middle East via Enon. DARPA Pegasus project underway will result in Part 108 compliant product. We're looking forward to that. That might be even a larger opportunity, we'll see. And then we're pursuing also short takeoff and landing VTOL projects for the Department of War. Please remember that the Wefunder campaign is still going on, and we're very close to the target that we have. Consider us for investment, and we hope that we kept you entertained today and we offered you sufficient information for the future. So thank you very much for your attention. Back to you, Simina.
Yes, thank you. So if attendants have questions, they can post them in the Q&A box, and we'll take them in as they come. One question that I think arises is on the exit plan and liquidity, which is something that it's a question we get quite often, and we are thinking about potential alternatives, including a direct listing. So that's something that's very much on our minds as well. And in terms of the markets that we're targeting, we think that our initial technology it fits very well with the new Part 108 opportunities, with the commercial cargo opportunities demand that we're seeing in Asia, and with the new Department of War focus on various aspects of drones. Um, the passenger aviation leg will come naturally out of that, as we grow the next aircraft size, which is a 2000. And
Simina, we have a question from Pete about the
yes,
IPO anticipated when and at what
yeah.
milestone. You want to address
Well,
that?
I think we're. I don't. I think it's something we're not going to put uh, a calendar milestone on it right now. It's something we are actively considering. And remember also that um, the path to liquidity isn't just necessarily an IPO. You also have direct listing and SPAC alternatives, both which are both ways of setting yourself up for uh, ongoing capital raises and providing liquidity to the existing investors. So Ben asks a very interesting question, which is the kind of uh, optimizations that we see in the future in terms of weight, 3D printing, electronics, fuselage, software controls. Andrei, I
Yeah.
think this is
Yeah.
for you.
Yeah, no, this is a great point. Absolutely, we have room for optimization in all of the above. 3D printing. So, for instance, I just shared with you the structure of the frame, the tubular frame of the DARPA application, the less than 55 pounds system. But we really think that there's a lot of room left to optimize, to use, to use an expression, sort of create a spine of the system made out of carbon, 3D printed carbon structure that of all the elements, Christmas treeing out of it and minimizing the weight of that. So obviously, we didn't have a lot of time for the DARPA system, but there's a lot of optimization left to be done for this system. It's related to what we call productization. So basically, we're flying this prototypes, but in the end, we will have to optimize the system as well.
And in a sense, the DARPA constraint is more difficult than a real world constraint because under Part 108, your total aircraft with payload has to be 110 pounds. But shaving grams to make it 55 pounds pre-payload is sort of the DARPA hard objective that we've set ourselves, and we seem to be going along fairly well on that. Pete asks about more details on the J2000. We think that we'll be in a position to start first tests of that in late 2027. And Andrei, if you want to comment on in what ways it's easier than the 500.
Yeah, it's first of all, I want to point out the fact that the thrusters we used in the rear, the swiveling thrusters that we use in the rear of the J500 are actually identical to the front thrusters of the J2000. So there is no need for development there. The biggest development will be the rear thrusters of the J2000, which will be 1,000-pound force class system, and of course the engine. We have several candidates for the engine. The engine will be based on either a PT6 made by Pratt& Whitney or a G Honda turbofan, whereas instead of using them as turboprop or fan, we will actually extract the air from the bypass fan or replace the prop with a turbo compressor we have to develop. None of what I just said is new invention or something out of the box. Everything is very well understood. Axial compressors have been developed since, the invention of the turbine. So we're pretty optimistic there. But yeah, this is the timeline, and the longest development will be probably the adaptation of an existing certified engine, such as the G Honda HF120 or the PT6 family of engines. Remove the reduction gear and the propeller and turn it into a turbo compressor or turbofan. I use that interchangeably because that's what it is. So as far as the airframe, we can tell you that number one, we had tremendous interest from even from two Italian companies that have been doing the modeling of Ferraris, and we've been approached by both Pininfarina and Ital Design to do the interior design of the system and the external design. We have, of course, not picked one yet, but there's tremendous interest there in terms of the style of the system as well. So that's where we're at with the J2000. We're encouraged by the development of the front thrusters already, and we feel pretty confident that the system will be naturally scaled up to the J2000 and beyond.
Under the new Mosaic rules, we can actually offer the G2000 as an experimental light sport vehicle. So start making sales before the commercial certification. But as Andrei said, we're starting, with the sort of the big lift, which is the engine. We're starting with well-known, certified uh, equipment from either Pratt& Whitney or GE.
Uh, there's a there's a question from Bill Pentler. Bill, thanks for the question. So, being an older person and thinking in a light-hearted way, I realize hugely outside the current uses. Has anyone ever considered your design to fulfill the 60s science fiction goal of creating a jetpack? We have actually, believe it or not, we've looked into that, and we're very well positioned to do this, but we have to pick the projects that will bring us revenue as soon as possible. Jetpack is totally possible. The What we did in terms of close to a jetpack is a parafoil system that can actually transport the person. So that's something that we worked on actively on several military programs. And yeah, that work will continue. So parafoil, not jetpack, and producing a propulsion system that is less noisy than a propeller. Carlos is asking, compared to Jetoptera's conventional FPS architecture, where do you see the practical ceiling for a pure battery electric aircraft? Okay, so we've been explaining that our system is energy agnostic, and in terms of using a battery-only system, we actually don't see that happening anytime soon, because you will have to develop a battery that, in our opinion, it's at least 1,000 watt-hour per kilogram. But even so, as I just explained, the range, a battery, as you lose weight with a fraction of fuel on board, you can go further and further by a logarithmic law. So it's not it's not a linear dependency. As you get lighter, you can fly further and further. With a battery, that's not the case. You're limited severely in there. And this is where, even if you increase the battery energy, specific energy system to 1,000 watt-hour per kilogram, there's a danger of packing so much chemical energy in a small package. So we think that we're going to stay with the turbine for quite some time before we actually consider a battery. But that's not the problem. We have actually tested battery-driven compressors with our system. Ben is asking, what will be the award for winning the DARPA challenge? Okay, so the DARPA challenge will award $2.5 million for the winner if you can complete that Mission Impossible circuit that they concocted. which is 4 miles and 22 turns linearly. If you complete that with less than 4 times the weight, then you will get half the price. So that would be $1.25 million. And there are other awards. I don't remember all of them, but for the unique aerodynamics, you get $500,000, and for unique propulsion system, you get $500,000. That is to be determined by DARPA, so that's all we know at this time.
But as Andrei said, we look forward to demonstrating flying with the payload and doing the 4 miles and but doing it in a circle, which makes more sense. The 22 turns, it is the it's going to make for exciting viewing, but it's obviously it introduces extra fuel needs that we're not very excited about, but we'll do it.
Well, looks like we're 4 minutes over the time. Hopefully, this webinar help everybody, understand more about our technology. And then we'll continue having this webinars. But Simina, any last concluding remarks?
No, thanks everyone for your time. Recording of this will be made available, and thank you for joining us.
Thank you very much.
Bye-bye.